Harvard astronomers have sounded the alarm. A rare interstellar comet, 3I/Atlas, is no longer just passing through our solar system. It's now on a trajectory bringing it closer to Mars.
Simply because it doesn't pose a threat? Or would I be happier if it's an alien technology? I have a hard time deciding, but as a scientist, I want to figure it out.
It began, as many cosmic stories do, with a silent traveler emerging from the darkness between stars. Astronomers observed a faint, shifting glimmer in the sky, an object hurtling along a path foreign to anything from our solar system. This was 3I/Atlas, a comet with peculiar velocity and trajectory, marking it as an interstellar visitor. Unlike the icy bodies orbiting our Sun from the frigid Oort cloud, 3I/Atlas showed every hallmark of a distant origin, drawing scientific attention from observers around the globe. At first, calculations showed that 3I/Atlas would pass Mars by a comfortable margin, a cosmic tourist traversing the solar system before fading back into the void. For months, teams at NASA and Harvard tracked its arc, refining models with each new observation. Their early simulations suggested little reason for alarm. Other interstellar objects had been detected before, such as Oumuamua and Borisov, each leaving more questions than answers, but never posing a danger. Then, the data shifted. As more telescopes contributed and astronomers improved their measurements, the projected path of 3I/Atlas drew steadily closer to Mars. Some researchers, including a team led by Harvard astronomer Avi Loeb, flagged new, more precise calculations. Their models suggested the comet would approach nearer to Mars than previously expected, a prospect carrying considerable implications, especially for the robotic explorers orbiting and inhabiting the red planet. News of the potential close encounter spread quickly, raising questions and triggering debate. Would humanity witness an unprecedented close pass, perhaps even an impact between Mars and an object that originated outside our solar system? What would be the consequences for Martian exploration? And what might such an event teach us about planetary defense and cosmic hazards? The discovery of an interstellar intruder. The significance of 3I/Atlas is best appreciated in light of its discovery. Astronomers detected it via the Asteroid Terrestrial Impact Last Alert System, ATLAS, a telescope array designed to spot and track objects that might impact Earth. This comet, however, quickly stood out. Its high velocity and sharply angled trajectory meant that 3I/Atlas was not gravitationally tethered to the Sun, but was instead passing through, originating from the realm between the stars. This unusual orbit earned it the 3I designation, third interstellar object ever witnessed by astronomers, following the discoveries of Oumuamua in 2017 and Comet 2I/Borisov in 2019. The comet's motion was documented meticulously, with teams analyzing its light curve, spectrum, and precise trajectory. With every new data point, astronomers in both public institutions and amateur circles refined their models and debated the implications. Early orbital estimates placed its closest approach to the Sun, perihelion, around October 30th, 2025, at a distance of about 1.4 astronomical units, or approximately 210 million kilometers, 130 million miles. As for its approach to Mars, initial data suggested a wide berth. Yet subsequent observations and improved calculations, particularly from a Harvard-led group, revised those numbers. The minimum distance narrowed, first to a few million kilometers, and ultimately to an estimated 1.95 million kilometers from the Martian surface. On terrestrial scales, this gap seems enormous, nearly 5 times the distance between the Earth and its moon. But in the context of interplanetary travel, with the comet's enormous velocity and uncertain trajectory, even a tiny observational error could have substantial consequences. This uncertainty gave rise to concern, not just about a direct impact, but about the potential hazards for spacecraft orbiting Mars or operating on its surface. Data gathered from ground-based observatories and solar system missions, including spacecraft observing from proximity to Mars, Jupiter, and even the Sunday, contributed to an ongoing stream of refinement. Amateurs and professionals alike pooled resources, watching for changes in the comet's outgassing, trajectory, or unexpected behaviors. For planetary scientists, the comet's approach represented both opportunity and risk, an occasion to study an ancient outsider up close, but also to confront the possibility that Mars might be in the path of something far more dramatic than a passing visitor. The tipping point, revised calculations prompt, caution. After Harvard's Avi Loeb and his team reported their recalculated trajectory, more scrutiny followed. The group highlighted that 3I/A TLAS's new projected path would bring it far closer to Mars than previously thought. Loeb, known for both his scientific acumen and willingness to explore provocative ideas, flagged the close approach as a potential planetary defense concern. His warnings and public statements ignited discussions throughout the astronomical community. The reported closest approach date, October 30th, 2025, prompted further analysis. According to available calculations, the comet would come within 1.95 million kilometers of Mars. While still a considerable distance, the tiny margin for error inherent in measuring the orbit of a fast-moving, outgassing comet from deep space justified caution. Unanticipated forces, such as outbursts of sublimating gases or gravitational nudges from nearby planets, could slightly alter its path. NASA and researchers at other institutions reviewed the data. The overwhelming consensus was that, based on current orbital models, a direct impact was highly improbable. Still, the prospect of a large interstellar object coming within a few million kilometers of a planet was rare enough to warrant attention, particularly because Mars hosts an array of valuable scientific spacecraft, both orbiting and on its surface. A potential collision, even though remote, was theorized to be catastrophic. An object of this scale and origin, moving at interstellar speeds, would release energies far exceeding the most powerful nuclear weapons, gouging a deep crater and distributing ejecta widely. The loss of scientific infrastructure, mission data, and potential future exploration capabilities would be significant. Such scenarios spurred mission planners to evaluate contingency measures for their robotic assets, including trajectory updates and possible sheltering maneuvers. What is clear, while astronomers could not predict with absolute certainty the exact trajectory until much closer to the date, the revised risk projections elevated 3I/ATLAS from curiosity to a genuine cause for careful observation and planning. Evaluating the possible consequences. What could happen if a comet like 3I/ATLAS were to impact Mars? While the probability remained very low, the theoretical consequences were grave enough to merit serious consideration and public discussion. Estimates suggest that a collision could release an energy equivalent to millions of nuclear bombs. The resulting crater could measure up to 60 kilometers across, dwarfing many seen in recent geological history. The immediate aftermath would include widespread ejection of Martian dust and rock, alterations to the local atmosphere, and a wave of shock heating radiating from the impact. While no human lives are at stake, Mars's most advanced robotic sentinels would be vulnerable. Orbiters could be damaged or destroyed by debris fields. Landers, including those critical for ongoing studies of Mars's geology and atmosphere, could be buried or rendered inoperative. Future missions might be forced to delay or adapt to new orbital hazards, showing how even a near miss by an object of this magnitude could alter the trajectory of Martian exploration. Scientific speculation extended to possible environmental effects. A sufficiently large impact could potentially excavate subsurface ice, causing melting and temporary flooding in the crater's shadows. Some hypothesize that such impacts could have long-term consequences for Martian climate, though the dynamics are highly uncertain and remain a topic for further study. Nevertheless, the primary concern in the short term would be the safety of scientific probes and the loss of invaluable data on Mars's ongoing processes, debates, and unusual hypotheses. With the approach of 3I/ATLAS, scientific debate flourished. Avi Loeb, in particular, drew attention not only to traditional planetary defense concerns, but also to unusual hypotheses. Loeb speculated publicly that the object, with its curious luminosity and anomalous properties, might be something more than a chunk of rock and ice, possibly a relic or even an artificial probe from another civilization. NASA and the wider astronomical community responded with skepticism. Most experts attributed the comet's observed luminosity to natural causes, sunlight reflecting off exotic ices or unusual outgassing behaviors typical of dynamically new comets entering the solar system. NASA publicly dismissed the idea of alien technology, emphasizing the need for evidence and adherence to established scientific protocols. Nevertheless, the very act of exploring these contentious ideas spurred serious discourse. Some researchers considered physical irregularities in the comet's path, questioning whether non-gravitational processes like asymmetric outgassing could significantly alter its motion. Others examined spectral data for novel compounds. The debate broadened the public understanding of how interstellar objects are characterized and the limits of our current detection abilities. What stands out is that while bold conjecture captured imaginations, scientific caution and robust data analysis remained at the forefront. Any claims of artificiality demanded extraordinary evidence, and the community as a whole remained grounded in first principles until clear, confirmatory evidence emerged. Readiness, response, and the global conversation. As the date of closest approach drew near, NASA, ESA, and other space agencies monitored both the comet and spacecraft around Mars with increasing vigilance. Teams conducted assessments of assets in Martian orbit, evaluating potential risks resulting from either a direct hit or a significant increase in meteoroid debris density during the comet's flyby. Given the enormous velocity and mass of 3I/ATLAS, planetary defense options for deflecting an object at that scale and distance were essentially non-existent with existing technology. Most actions centered on preparation, running impact simulations, developing strategies to protect critical data, and laying plans for future recovery should an adverse event occur. These preparations prompted a broader discussion about planetary protection, expanding not only to threats facing Earth, but to the assets and scientific legacy on Mars. Key questions included: how resilient are our probes and orbiters to high-velocity debris? Could we meaningfully shield or reposition spacecraft in time, given mission constraints and communication delays? How should future missions incorporate redundancy in the face of such low probability but high-impact hazards? Ideas for contingency response ranged from deploying rapid response missions with time-critical science goals to developing more robust warning and tracking systems for future interstellar objects. The scientific community saw renewed interest in applied planetary defense, not just for Earth, but for all worlds under robotic or future human occupation. Countdown to the encounter, October 2025. By mid-2025, 3I/ATLAS was under round-the-clock scrutiny. Astronomers worldwide contributed observations using ground-based and orbital telescopes. Probes near Jupiter and the Sun transmitted additional data, refining orbital parameters as the comet neared its perihelion and its closest approach to Mars. NASA and partner agencies updated mission teams with the latest risk projections. While the consensus was that a direct impact was highly unlikely given best estimates, the possibility of new variables, such as unexpected outgassing or a last-minute gravitational perturbation, could not be entirely ruled out. Mission planners prepared both for a nominal close approach and for the low probability scenario of a catastrophic encounter. On the ground, Mars's robotic explorers continued their tasks, recording local seismic and environmental data. Engineers prepared for possible service interruptions, working to ensure that, even in the event of damage or loss, valuable science could be preserved and transmitted before the comet's passage. Debate in scientific circles and the public sphere shifted focus. Would 3I/ATLAS pass by as a remarkable but ultimately routine interstellar visitor, or would it leave an observable impact on Mars's surface or environment? Journals, conferences, and popular media discussed not only the mechanics, but also the lessons for future mission resilience. Whether impact or near miss, learning from 3I/ATLAS. Regardless of the final outcome of 3I/ATLAS's encounter with Mars, be it a dramatic impact, a grazing pass, or a wide miss, the event's legacy for science and planetary protection remained assured. In the event of a direct or near-direct hit, new data about the impact itself would be quickly captured by surviving orbiters and relayed to Earth. Scientists would analyze changes in Martian surface composition, atmospheric chemistry, and local climate effects. Any new crater could be analyzed remotely, offering a modern model for understanding historical impacts that have shaped both Mars and the Earth. If the comet missed Mars entirely, the careful preparations and improved models would not be wasted. They would be incorporated into future mission designs, enhancing resilience and driving investment in improved detection and response programs for potentially hazardous objects, both native and interstellar. The debate over 3I/ATLAS's artificiality, though not supported by the bulk of evidence, illustrates the openness and rigor of the scientific process. It forced the community to articulate standards for extraordinary claims and prompted a re-examination of how subtle, ambiguous data should be interpreted and communicated. Perhaps the most valuable legacy lies in the shared sense of humility and preparedness. Each encounter with a cosmic interloper, even one passing at a safe distance, reminds us that the solar system is not isolated from the wider galaxy, and that the pace of discovery demands both vigilance and adaptability. A continuing cosmic story. As 3I/ATLAS exits the inner solar system, astronomers and the public alike are left with new insights and renewed vigilance. The episode underscored both our technological limits and the importance of international cooperation in planetary defense. Large-scale hazards, no matter how improbable, demand readiness and open lines of communication between scientists, agencies, and the public. The event marked a milestone in our ongoing relationship with interstellar objects. Each detection, analysis, and cautious recalibration brings us closer to understanding the full range of cosmic risks and opportunities in the solar neighborhood. Finally, the story of 3I/ATLAS represents more than just a data point or a risk scenario. It is a living example of the power and limitations of 21st century science. It demonstrates how curiosity, careful analysis, and creative approaches to problem-solving come together as we watch the skies, seeking not just to understand the universe, but to ensure the survival and flourishing of intelligent life within it. In conclusion, cosmic perspective and preparedness. The rare approach of 3I/ATLAS to Mars, whether it results in a routine flyby or something more consequential, has woven a narrative blending vigilance, scientific rigor, and imagination. Confronted with both uncertainty and potential, the world's scientists, engineers, and planners responded not with panic, but with careful calculation and open-minded study. The fundamental lesson is clear. While collision probabilities for interstellar objects are extremely low, their potential consequences warrant ongoing investment in observation, coordination, and planetary defense, not only for Earth, but for the broader realm of solar system exploration. The stakes of planetary stewardship are rising as humanity's reach expands. As long as the universe continues to send us enigmatic travelers from far-off stars, we are challenged to seek knowledge, improve our defenses, and embrace wonder. The tale of 3I/ATLAS, wherever it ultimately leads, will serve as a reminder of both cosmic fragility and human ingenuity. If you're fascinated by cosmic mysteries and the unfolding science of exploration and defense, consider staying engaged and informed. The story is far from over. New objects, new questions, and new discoveries await just beyond the edge of sight. Ensuring our drive to explore and understand the universe will continue, propelled by curiosity and sharpened by preparedness.